All right, in section 12.5, we talk about absolute extrema. So an absolute extreme, as opposed to a local extreme, the absolute is the biggest or the smallest for the whole function. Okay? The local extreme, they were the minimum in this little area here, and then you could have another minimum somewhere over here, and that's another local minimum, and then it could be even further or even higher. Whatever. That was on a very local basis. The absolute extremes, those are the ones that are the biggest or the smallest throughout the whole thing. Some terminology. Some people like to use the word global. Global or absolute. So if I accidentally say global max or global minimum, that's the same thing as an absolute max and absolute minimum. Okay. Definition. If f of c is greater than or equal to f of x for all x in the domain of f, then f of c is the blank of f. So here, f of x is just sort of every function value possible, and f of c is one particular y value that is larger than all the other values. If that is the case, then we say that f of c is the absolute maximum of f, or absolute max. And then, of course, if we have the reverse, f of c is some y value that is less than every other y value in the domain of f, then we call that value the absolute minimum. Now, certainly it's possible that the absolute max or absolute minimum could occur at different points, okay? But when we talk about the absolute maximum value or the absolute minimum value, we are talking about the y value. Let's take a look at these examples in example 1. Here we have a graph. We can tell by the end behavior on the left that this graph will go to positive infinity. It has some wiggling in the middle. And the end behavior on the right, the graph goes to negative infinity. What could we say about the absolute maximum, and what could we say about the absolute minimum? Do we actually have any of these? And the answer is no. There is no absolute maximum because the graph, based on the arrows, continues to rise as it goes to the left. So there is no largest y value. And here, there is no absolute minimum. That would be the smallest y value. It keeps going down to infinity. What about the middle graph? Do we have an absolute maximum? No absolute maximum. It continues to rise. What about an absolute minimum? Yes. And what is that absolute minimum value? Take a shot at it. Yeah, it's -3. Okay. Now, just like we did with the local min and max, you could say, add x equals, and I'll just guess that that's -1.5. But when we talk about the absolute minimum value, that is the y value. Okay? This is where this stuff comes in for business. You're going to be looking at maximum profit, minimum cost, maximum revenue, things like that. So you're looking for the absolute max and min for those. All right, go ahead with your partner and do the third one. All right, Zach, what did you get for the absolute maximum? 5. Where does that occur? All right. And Carla, what did you get for the absolute minimum? And where does that occur? X equals 3. Very good. All right, so you notice that this last one had both the absolute maximum and the absolute minimum. What is something fundamentally different about the last one that the first two it changes sort of dramatically? And thus, in the first two, we didn't have both the absolute max and min. Yeah, it's a closed interval, and that's it. So it's closed because it has a point here, and then it's stop in the middle. Here we had arrows that continued on forever. It's not closed. Here, continues on forever, not closed. That leads us to the extreme value theorem. The extreme value theorem says a function that is continuous on a closed interval must have both the absolute max and the absolute minimum on that interval. Okay? So that's why we knew that this third one was going to have both of them, whereas one of these others, they did not have both of them. All right, so a closed interval, continuous function, gives you the absolute maximum and the absolute minimum. Next page. For example 2, we have f of x is equal to x squared, but it's x squared only on the interval -2 to 3. You can see I've drawn for you from -2 to 3, but I've also sort of given you the dashed version of everything else. What is the absolute maximum value of this function on this interval? 9. And where does that occur? X equals 3. What about the absolute minimum value? 0 occurring at 0. Okay. Now, a function is highly dependent on its domain. So if I change the domain of this function, and now we use the interval from 1 to 3, that has the potential of changing the absolute extrema. Go ahead with your partner and find the absolute extrema for example 3. And state where the extreme value occurs.
No,
So you might get this one. Okay. But remember, it's absolute minimum. Yeah, if it keeps going, then you don't have a maximum. All right, let's check it. So the absolute maximum, Matthew, what's the value and where does it occur? Okay, so that one was the same. And minimum, Daniel, what'd you get for absolute minimum?
1 at x equals 1.
Yeah. Yeah. So the difference between these two is that the minimum on the first one occurred at the vertex because we were able to get down and then turn around and come back around. On the second one, the vertex point is not included in the domain. So you don't even get that far down. How would you describe, in calculus terms, this vertex point? What is this as it pertains to that function? I'll give you a hint. Its initials are CV, critical value. So the points that we get for these minima and maxima, they're either the critical values or they are the endpoints of these graphs. And that's our next theorem. Absolute extrema, if they exist, must occur at critical values or the endpoints of an interval. Okay. So when you're given a closed interval, this is closed interval here, and you're given a closed interval, in order to find the absolute extrema, you need only check the endpoints and the critical values. Let me demonstrate. Let's start with f of x is equal to x cubed minus 6x squared minus 15x plus 5, and first on the interval from -2 to 8. So let's go ahead and find the critical values. We find the critical values by finding the derivative. And then setting the derivative equal to 0. So 3x squared minus 12x minus 15 equals 0. It's a quadratic, so I will factor. I see a multiple of 3 everywhere. So it's going to be 3 times x squared minus 4x minus 5 equals 0. Factor. So we get 3 times x minus 5 times x plus 1. I get a solution of x equals -1 from this right factor. What about the x minus 5? X equals 5. What about the 3? Which is? Nothing. Yeah. So that's no good. So these are the critical values. Now, you need to determine if you have absolute min or an absolute max, or if it's just some other value. And the only way to do this is just to test all the values. You have 4 values to test. You need to test the critical values and these endpoints. So f of -2, and I've worked these up ahead of time. That would be a 3. And I'm just plugging these into the original function. It's f of a value. What's the other endpoint? 8. F of 8 is 13, so these were the endpoints. Now the critical values. F of 5 is -95. And f of -1 is 13. We are testing because we know that the absolute extrema occur at either the critical values or the endpoints. I just don't know which is which. So I got to figure out which ones are the biggest and which ones are the smallest. So the -2 and the 8, where did those come from? No. That's the interval. See, we're graphing this function, this original function, only between -2 and 8. So it's going to look something like this. I don't know exactly what it looks like, but you know, it's something like this, maybe. You just don't know if it's like this or if it's like this, and then that's the highest point and whatnot. You don't know what it looks like. Okay. All right. So winners and losers here. So -95, that's the smallest. So that's the absolute minimum. And then what is the largest? 13. We have a tie. That's okay. It just means it occurs at 2 different points. Much like the sine function, if you're familiar with trigonometry, it takes on its maximum all over the place. So the absolute minimum is -95. That occurs at x equals 5. The absolute maximum is 13, and it occurs at both -1 and 8. Questions?
Why didn't you test 3?
That's the next problem.
What?
That's the next problem.
Oh.
Yeah, see? Do it in here. That's part A, part B. You're going to do part B. Okay, do part B. So now you use the same function, but you do it on a different interval. You do it on the interval from -2 to 3. But it's the same function. So you can already use some of the work you already have. All right. So what did you get for the absolute maximum?
The absolute maximum I got value of 13 and only had x equals 1,
Mm-hmm.
1 and 8.
Yeah. What's the absolute minimum?
Negative 67 at x equals
3?
wrong.
Yeah. Yeah. So what happens here? So now you're only on the interval from -2 to 3. What are your critical values? Just -1. The x equals 5 is no longer available because it's not inside that interval. So the max occurs. So you still have f of -1 is 13. That's the absolute maximum. You have f of -2, which is 3 still, and now you have f of 3, which is -67. That's your absolute minimum. All right. So your critical values are reliant on the domain in which you are working. Questions over that example?
You want to give us the remaining of where they're at, which is open domain.
It's the largest domain possible. Yeah. All right, page 3. All right, let's fix part of this. And this is called the second derivative test. It says let C be a critical value of f. This is supposed to say f prime of C and f double prime of C. So what you're doing is you're testing that critical value, that number, in the first derivative and the second derivative, and then we see what happens. So, and we're going to assume that these critical values are come about from the derivative being 0, not the derivative being undefined. Okay? So f prime of C is equal to 0 in all cases here. Now, we have some choices to make about what could happen with f double prime. Suppose that f double prime of C is positive. Right? We're making a full chart here. So suppose it's positive. What can you tell me about the graph of f at that point? Concave up. It is concave up. Because the second derivative at that point is positive. Okay. Well, what do we have? We have f prime of C is equal to 0. So we have a horizontal tangent line. We have concave up. So it must look like this, right? With this point being C. So what can you tell me about f of C? So local minimum. We don't know if it's absolute yet. We know it's at least a local minimum. It may turn out to be an absolute minimum. We don't know. All right, let's run the scenario again, this time with a second derivative that is negative. What can you tell me about the graph of f? Concave down. The picture would look something like this. Concave down with a horizontal tangent line at that point, thus producing what? Local max. And then lastly, if the second derivative evaluated at C is also 0, that does not tell me anything about the concavity, and the test does not apply. So this is called the second derivative test. Basically, it says the following. If you want to know whether or not you have a local min or a local max, you take your critical value and you plug it into the second derivative. If the second derivative is positive, that means you had a concave up function giving you a local min. Right? And if you plug it in the second derivative and you get a negative, that means your function is concave down, which means you had a local max. All right. Example 5. Use the second derivative test to find the local extrema of f of x equals to 2x minus x cubed plus 5. So first we need to find the critical values. Critical values come from the first derivative set equal to 0. So this would be 2 minus 3x squared. Set the first derivative equal to 0. Solve for x. So x is equal to plus or minus the square root of 2/3. And we won't rationalize or anything, we'll just leave it like that. Now we want to know what happens at x is equal to positive square root of 2/3 and negative square root of 2/3. Is it a local min or a local max? To find that, we need the second derivative. Second derivative is negative 6x. So let's test both of these critical values in the second derivative. So f double prime of square root of 2/3 is negative 6 times the square root of 2/3. And that's going to be a negative. It's a negative times a positive. So it must be negative. So that tells me that at x equals positive square root of 2/3, f of the square root of 2/3 is a local, and then what is it? If the second derivative is negative, that means it's concave down, which is a local max. In theory, you should work this out, but I'm just trying to show you the principle here. And then work out the other second derivative. That's positive because it's a negative times a negative. And then write out your conclusion based on the second derivative test. And which one is it? That's a local min. Yeah. So it's second derivative positive, we have concave up, which is a local min. All right, questions on applying the second derivative test? All right, let's look at the next page. Now, how could we get an absolute extremum by using the second derivative test? Well, let's write it this way. If there is only one critical value second derivative test gives absolute extrema, not local. All right, so the second derivative test in general tells us about local extrema, local mins and local maxes. But if there is only one critical value, so there is only one critical value where it reaches the top and then it has to come back down, you know it's never going to be higher than that point because there's no place for it to turn around. Well, that must be the absolute maximum. Same thing here. If we have a critical value that was a local minimum, there is no other critical value for it to turn around, so that local minimum has to be an absolute minimum. So the key here is only one critical value. If there is only one critical value, then it does give us the absolute extrema. Example 6. Find the absolute minimum value of f of x is equal to the natural log of x quantity squared minus 3 natural log of x on the interval 0 to infinity. So first off, notice that we don't have a closed interval. We have an open interval. It's open at 0 and it's obviously open at infinity. So we can't use the extreme value theorem type stuff. We don't have a closed interval to test it with. So our best chance is to work with the second derivative test from above. So let's find the derivative. So we have natural log of x quantity squared minus 3 natural log of x. The first derivative here, we would bring the 2 down. The inside stays the same. Lower the power by 1. using the chain rule, times the derivative of the inside, 1 over x, minus the derivative of 3 natural log of x, which would be 3 over x. Combining these, they both have the same denominator, so we just add their numerators. That would be 2 natural log of x minus 3. We need to find the critical values. The critical values are when f prime is equal to 0 or f prime undefined. To set f prime equal to 0 is the same thing as taking the numerator and setting it equal to 0. Solve for x. I would move the 3 to the other side. Divide by 2. That's magic. And now to solve for x, you change it back to exponential form. Does everybody remember that natural log is log in base e? So this literally says e raised to the 3/2 power is equal to x. So the value of x is e to the 3/2 power. All right, what about the denominator? If you want to know where f prime is undefined, set the denominator equal to 0. That's x equals 0. Do we get to keep x equals 0?
Oh, no, because
Yeah, the interval is open at 0, so x equals 0 is tossed out. So that's good news for us, because how many critical values did we end up with? Just the 1. So that means we can use the second derivative test for extreme values. So here we go, right here. Here's the first derivative. So I'm going to take the second derivative. This would be the derivative of the numerator, which is 2 over x, times the denominator, unchanged, minus the derivative of the denominator, 1, times the numerator, unchanged, divided by the denominator squared. All right. So then we have 2 over x times x, that's 2. Distribute the negative, minus 2 natural log of x plus 3 over x squared, which is 5 minus 2 natural log of x over x squared. Now we're using the second derivative to test the sign at the critical value. We want to know if it's positive or negative. So we'll take the second derivative and we will plug in e to the 3/2 power. That would be 5 minus 2 natural log of e to the 3/2 power over e to the 3/2 power squared. And then we work this out. So the natural log of e to a power is just that power. So this is 5 minus 2 times 3 halves over e to the 3 halves squared is e cubed. Because you multiply the powers. E to the 3 halves squared is 3 halves times 2, it's e cubed. And then what is this? This is 5 minus 3, right? The 2's here cancel. Over e cubed. That's a positive. E cubed is positive, so this is positive. So what does that tell me about the critical value? Positive means concave up, which means absolute minimum. So F has an absolute minimum at x equals e to the 3 halves of, and I'll show you this calculation in a second, 2.25. That comes from this, taking e to the 3 halves and plugging it into the f function. So natural log of e to the 3 halves would be 3 halves squared minus 3 times 3 halves. It would be 9/4 minus 9 halves, which is negative 9/4. Oh, it's negative. Sorry, don't forget the negative. Negative 2.25.